Okay, continuing with our review on forces, we're going to look at Newton's second law. So Newton's second law states that the net force on an object is equal to the mass of that object times the acceleration of that object. That's all very well and good, but what do we do with it? So we're going to look at a classic problem. It's over here on the right. I've got two masses, just calling them M1 and M2. They are connected by a rope that goes over a pulley. And my question is, what is the acceleration of this system? Now, because they are connected with a rope, I can treat them as the same, they must have the same acceleration. It's just not possible to have anything else. So, the first step, always, in a problem such as this, step number one, well, free body diagrams. You may remember these from last year. Free body diagrams. And sorry, something's wrong with my computer and it's like jumpy, so I apologize. This might be a little choppy, this whole video. Okay, so a free body diagram is when you reduce an object down to just a dot to represent the object. Usually we label it with its mass. This is M1. And we write arrows to represent the forces acting on that object only. Now I've got two objects connected by a rope, which means I need two separate free body diagrams. Okay, so I'm going to have M1 and M2. Now, the forces acting on those, when I look at M1, I got this rope sticking out the top. So I've got this force of a rope. The force of a rope or a string or dental floss or whatever, we don't just call it any old force, we call that tension. Tension, T, come on. Notice M2 also has a rope sticking out of the top, so it will also have a tension T. Now in this particular case, the rope is the same that's connected to M1 and M2. If I had like two different pieces of rope, I would need to label these like T1 and T2. I think that's on one of your homework problems as well. Now, I also have, let's see, gravity is pulling on these. In fact, gravity will always show up somewhere in your free body diagram. It's always there. We can't turn off gravity. Now, I don't know if the gravity is the same as the tension, so I'm not going to draw them quite the same. For all I know, they are the same. I don't really know for sure. Okay, so this is the force of gravity. The force of gravity on this one, change the pen size here, is mass times gravity. In this case, the mass is M1 and then gravity. And the force of gravity on this one, again, I don't actually know how big it is, so anything will do. Oops, come on. That would be mass times gravity. In this case, the mass is M2 times gravity. Now, those are all the forces acting on these particular bodies. If we had other things going on, we'd add more forces. But that's it for free body diagrams for this particular problem. So we'll move on to step 2. Okay, step 2. You got to find the net force. Net force. Okay, so to find the net force means I've got to add things. Now, luckily for us, our forces are in the vertical dimension for both of them. That makes things easier. That means I can just add and subtract them. So the way that I typically do it, and this is a personal preference, you might have another way that you prefer. I have to do them one at a time, so I'm going to do M1 first. So for M1, the net force, oh, come on, computer. Okay. I'm going to write down all of them that point in the positive direction. Now, I established over here next to my picture that up is positive. So the thing that is up is T, so I write that down. If I had more, I would then add them, like plus whatever else is in positive direction. I don't have anything else though, so I stop there. Then I write minus, and I'm going to minus anything that's in the negative direction. So in this case is M1G. M1G, like that. Okay. Those are all the forces, so I would stop there. I can also do this for M2. Let's see, let's use, how about this funny bluey color here? Okay, so for the second object, well, I've got T pointing up again, and down I have M2G. Okay. Okay, step 3, kind of squeeze it up here to the living room. I'm going to use Newton's second law, so F net equals ma. Now this actually works in general, or I can use it individually for x and y. I only have y here, so I'm going to go ahead and throw a y on here just so I'm clear. Later, when we have things with forces in both dimensions at once, we will have to do the two dimensions separately. So that's kind of annoying. So from over here, I've got that F net of the first object is equal to T minus M1G. So I'm going to replace, instead of F net equals MA, I'm going to do T minus M1. T minus M1G, G equals mass of the first object is M1, and then acceleration. Okay. Now, I don't know if that acceleration is going to be positive or negative, but when I write the second thing, so the second one, this time F net is T minus M2G equals, and the mass is M2. Now, the acceleration is still A, but we have a little bit of a problem. I know that the number is the same both times because it's attached to a rope, but the direction should be opposite, because if M1 accelerates up, M2 has to accelerate down. So just to make sure that I know that it's opposite, I'm just going to throw in a negative on this thing right here. Okay. In the next step, I'm going to pull this negative out to the front so it's not, well, actually, I'll just do it right now. I'm going to put it in the front so that it doesn't look like M2 minus A, because that would be really wrong. Okay, so now I have two equations and two unknowns. I don't know T and I don't know A, but I know everything else. So since I have two equations and two unknowns, I can solve for T and I can solve for A, but I don't actually care what T is. Okay, I just care what A is. So what I'm going to do is I'm going to solve one of these for T. Let's see. Let's do, you know what, let's do the second one. So I'm going to add M2G to both sides. That gives me T equals, well, now I've got a positive M2G on the other side, and I'm left over with this negative M2A over here. Okay. Now that I know that, I can go and plug that T in the first equation right there. So then that would give me, I'm going to color code it. Yeah, here we go. That would give me M2G, oops, come on, minus M2A. And then I've just replaced just that T. I have to write the rest. Okay, so I've still got a minus M1G equals M1A, like that. Okay, I'm going to switch back to black now because I've combined the two colors into one equation. So yeah, I want A, so I'm going to get all the A's together on one side, and that'll leave stuff that doesn't have A alone on the other side. So leaving this one alone, M2G, that one I'm going to move over to the other side, so I'm left with minus M1G on the left equals, okay, I had an M1A on the right, and I just added M2A from the other side, like that. Okay, I'm going to go ahead and factor out what's in common on these two things. So over here, if I pull a G out, I get M2 minus M1, come on, G. And over here, I can pull an A out, and I get M1 plus M2 all times A. I'm going to divide by M1 plus M2 on both sides so that A will be alone. So I end up with M2 minus M, oops, that's an M, sorry, M1 times G all over M1 plus M2. That equals A. Notice If M1 and M2 are the same, I get a 0 on top right here. And so I get an acceleration of 0. Now that makes sense because I have two things are the same. They're not really going to pull on each other. They're just going to sit there. Okay. If M2 is bigger than M1, I get a positive answer for this, and that means that M2 would be moving down and M1 would be moving up, or accelerating, sorry, not moving, accelerating. You can't see me, but I'm doing this hand motion, never mind. Okay. And if M1 was bigger than M2, I would get a negative acceleration, so it would accelerate the other way. That is, M1 would go down, or it would accelerate down, and M2 would accelerate up. Okay, so this was a one-dimensional, typical Newton's second law problem. We will do more complicated ones next.